So our next speaker is Scott Page, who is a professor of political science, complex systems, and economics at the University of Michigan. And the discussant will be Karen Croxson, who is an economist from Oxford.
Right. Thanks. It's really great to be here. What I'm going to do in this talk, in some sense, is very pedestrian. What I want to do is walk through some of the micro-foundations of where collective wisdom comes from. And I'm going to present this in two different models. But first, just a tiny bit of advertising. I recently wrote a book called The Difference, and in that I talk about collective wisdom in three different ways: problem-solving, prediction, and preference aggregation. Here I'm going to be talking exclusively about prediction. So how is it when you have a group of people making a forecast or predicting what the outcome of a policy is going to be, how those things aggregate? So a quick outline. I'm going to begin with what are the standard statistical models of collective wisdom, or you might think of sort of accurate prediction. And these really come from two different disciplines. They come from political science and economics, sort of social sciences. And they also come from computer science in something called ensemble learning theory. So I'm going to present a couple different theorems from those literatures, but they're really the same theorems with different notation. Right? That way different people can get tenure in the social sciences and the computational sciences. Then I'm going to present a more cognitive model of collective wisdom, and this is joint work with Liu Hong. And this, instead of thinking of things as people sort of getting statistical, getting signals from a distribution, we're actually going to try and model the cognitive process that people use. And so the ultimate mathematics that we'll use here will be sort of more measure theoretic, more sort of like standard real analysis sort of mathematics. So if you want the sort of gone in 60 seconds version of the talk, what I'm going to end up arguing is the following, is that collective wisdom requires individual sophistication and collective diversity. And when I say collective diversity, what I'm going to mean is actually differences in signals or differences in models people use to construct those signals. Okay, so if we want to, so one of the things we've sort of talked a little bit about this morning is sometimes we get collective wisdom, sometimes we don't. Well, if we don't get collective wisdom, it's going to be because either people lack sophistication, right? That's the garbage in, garbage out, or we lack diversity. And so even though people are reasonably smart, if they're all reasonably smart in the same way, the crowd can't possibly be intelligent. Okay, so here's the standard statistical model. And these are the sort of assumptions you'll lay out. You'll assume there's some sort of outcome. There's a set of individuals, and each individual gets a signal, right? So this looks like mathematics. I apologize. But so we just assume that there's some outcome theta we care about, and each person gets a signal. And then there's some giant vector of signals, right? So we can give a signal for each person in the room. And then there's some joint distribution function. Given the state of the world, right, we can write down sort of the probability that people get pairs of signals. So the idea is sort of as follows. It's almost like I had a set of cards, and I'm just going to hand them out to each of you, right? And those cards are distributed according to some distribution function. All right? So how do we measure, then, how well a crowd does? Well, you can think of the squared error for an individual as just sort of how far is my prediction from the outcome, and you square it. Then you can take the average across people. So this is, in some sense, just how good is the crowd, right? How far are they on average, right, from the prediction? Then you can take the collective prediction, which is the average of all those people's predictions. Then you can take the squared error of that. And then you can also talk about the predictive diversity, which is just sort of, on average, how different are people from the average prediction. Okay, so you can think of this as just another way you can think of this as variance in predictions. But I don't want to call that variance because I'm going to call something else variance in a couple slides. So here's what in the book I call the diversity prediction theorem. And this says the following. If I take the squared error for the crowd, so this is the crowd's error, that's equal to the error, average squared error of the people in it, minus their predictive diversity. Okay? Now the important thing about this is it's a theorem. It's like the Pythagorean theorem. So it's always true, right? So one funny thing about sort of writing this book is I've had people send me data from companies and which they say, look, it works here too as well, right? And so I've sent them little pictures that said, look at this triangle with 5, 12, 13, that one works as well too, right? I mean, it's a theorem, right? It always is going to hold, okay? So when people say collective wisdom depends on sophistication and diversity, right, there's a mathematical sense in which that's very much true, right? The interesting thing, though, and I think this is what runs counter to intuition, is the coefficient on squared error and the coefficient on diversity, in some sense, are the same. So it's not like it's 100 times ability and 0.1 times diversity. They sort of enter into this equally, which I think is somewhat counterintuitive. Okay, so if you take Sirwicki and Galton's famous example of predicting the weight of a steer, right? He talks about them being within a pound of the weight of a steer. The crowd error is 0.6. The average error, this is squared, is 2956. So that means on average people are off by about 55, 56 pounds. But the variance was 2955. So what you get is an accurate crowd, right, that's reasonably sophisticated, that's also fairly diverse, right? So in every one of the cases, you can do this. It's just like, shooting fish in a barrel. Anytime you have a case where the crowd's accurate, right, and you plug it in, you get numbers that look sort of like this, okay? There's a couple of jelly bean jar experiments I have where the average error is like, 1 million by the time you square it. People are off like 1,000, but then the variance is also off by 1 million, and so it looks sort of much more incredible than this one does. Okay. From this, right away, you get the following sort of hint at the wisdom of crowds. Another way to think of the wisdom of crowds is that it's always going to be the case that the crowd's error is going to be better than the average squared error, right? Because the theorem says the crowd error equals average error minus diversity. So that means the crowd error has got to be less than the average error. Oops, that should go the other way. Sorry, this should go the other way. So what we get is that the crowd, in some sense, is always smarter than the average person in it, provided the crowd is diverse. All right. So let me move on then quickly. Let me make a more expansive model. So now let's suppose that each person has this signal again, but there's a mean to that signal. And I'm also going to say there's a bias possibly to that signal. It's the difference between the mean of the signal and the true value. There's also going to be a variance to the person's signal, which is just sort of like, on average, how far off is it from the true answer squared? So I can think of there being an average bias, an average variance, and then I can think of an average covariance of the signals as well, like how much do the signals covary. Now I can write another theorem down. Then this one comes more from computer science, although some social scientists use it, which is the bias variance decomposition theorem, which comes from ensemble learning theory. And that says the crowd squared error is equal to the bias squared plus 1 over n times the variance plus n minus 1 over n times the covariance. Okay? Now, if covariance is negative, which would mean when mine's high, yours is low, right, then we'll get that the crowd is actually sort of better than the people in it. Okay? Now, when you first look at this seems to contradict the other theorem, because the other theorem said diversity was good, and this theorem is saying variance is bad. Okay? But this paradox is easily resolved. In the diversity prediction theorem, we're saying predictive diversity in that case is realized diversity. So it's actually differences in our predictions. So if our predictions differ, right, that diversity is good. Right? In the bias variance decomposition, variance corresponds to sort of noisiness in my prediction. Right? So the noisier my prediction, the worse we're going to do. Right? So if my prediction tends to be really noisy, we're not going to do as well. However, negative covariance, right, in the distribution is going to improve accuracy, right? And negative covariance is basically saying that we're likely to make different predictions, right? So in the bias variance decomposition, the negative covariance is playing the role of diverse predictions. So this is just sort of, in some sense, micro-foundations of the other theorem. All right. But here's where we get some sort of funky stuff. So one thing we get right away is there's this large population accuracy thing that comes out of this way of thinking. If I have a whole bunch of people, and if I assume on average they're not biased, then the bias will be 0, right? If I assume that they're getting independent signals, then the covariance will be 0. And if they've got some bounded variance, if I bring enough people to the table, eventually this 1 over n gets really, really small, and I get that the crowd's always going to be correct. So if I have this statistical view of just handing people out signals from a distribution, I get this sort of perverse result that we're always going to be right in the limit. And if you look in journals in these strange fields like political science and economics, they always have results that show for large populations the vote is always correct. And in some sense, this is why. Well, in some sense, this is exactly why. Right? Because they're basically assuming independent signals with no bias, and so as a result, everything's going to aggregate. Okay? Now, suppose people differ in how accurate they are. So let's let accuracy be 1 over the variance. Now, you could say, should people talk to one another, right? Should we talk to one another and put like maybe more weight on someone's signal? Right? So if we're sitting around talking and we hear, for example, that Karen makes a better argument, so we should put more weight on her. Well, it's actually then easy to show the weight you should put on someone is basically proportional to sort of their accuracy over the average accuracy, right? So if someone's more accurate on average, you just put more weight on them. Okay? Now, one reason we do the math, one reason for writing these mathematical things down is obviously like impress your colleagues and get tenure and that sort of stuff, right? But the other reason it helps us think through sort of logical flaws in our reasoning. So one flaw might be you'd think, well, we don't want to have people talk to one another because people might be, influenced by other people, right, who aren't accurate. So here's a very simple model that P.J. Lamberson and I wrote. Let's suppose that people have charisma that belongs to some range, x minus x, or little x, big X. They've also got accuracy, which is in W, little w, big W, right? So there's some range of accuracy and some range of charisma. So when somebody's making an argument, like let's say it's Dan, right? He's making an argument. He might not be accurate at all, but he might be incredibly charismatic. So as a result, his influence might be really high, right? Alternatively, John might be really accurate, but not charismatic, and so his influence would be moderate. So if I'm rational in that setting, and I can't, so all I'm getting is this sort of notion of influence. If I'm rational in that setting, what I should do is I should basically just assign to people the average charisma, right, and sort of subtract that off their accuracy. But then I have to do this maximum thing here because I know that their charisma couldn't be, this is like I know that their true charisma couldn't be bigger than G minus X, right? I mean, I know this is the biggest charisma could possibly be, right? So I've just got to sort of account for that. Well, if I do that, then what you show that setting weights proportional to these things actually outperform simple averaging, right? So at least in this model, the idea that, like when Sir Wiki says, other people say you shouldn't have people talk because you get worse outcomes. If you assume people are sort of rational enough to sort of say, well, look, I'm not going to put too much weight on that person, but it is a compelling argument, what you get, in fact, is the communication does improve outcomes. Okay. So what's the problem with that story, right? Because, I mean, this is what's in all the political science and economic journals and all the computer science journals. And here's the problem with that story. Where it came from initially is studies on luminosity of stars. So when they were measuring the luminosity of stars, there were people that had light meters, and they were different parts of the globe, and they would get readings of how bright those stars were, right? And we'd add those up. Now you can think of those as independent signals, right? So let me do some like real descriptive science here. Physicists tend to smoke pipes and cigars. So if Einstein's sitting over there and he's looking at the luminosity of a star, there's some true L, right, up there. He's going to see L minus epsilon. Why is he going to see L minus epsilon? Because there's little smoke, right, filtering out the luminosity. But Lord Keynes over here, right, he's an economist. He's going to stand under a streetlight because that's what economists do. So he's going to see L plus epsilon. So the story we tell, and it's interesting when you talk to people in finance in particular, it's hard for them to realize that there's any problem with this. And it's also true among, I think, a lot of economists and political scientists. This is just our standard model. We assume people get signals, and the signals are sort of like some model plus an epsilon, right? Well, the thing is, let's think about now, and that makes sense for the luminosity of the star. I'm not saying it doesn't. But when Google went public, it was not the case that everybody stood in Silicon Valley and went like this and felt G shining on down upon them, right? And some people felt G plus epsilon, and some people felt G plus epsilon, right? That's not at all what happens. What happens is the following. And so in the luminosity case, you get these nice bell curves, everything's fine. What happens is you get something that Lou and I call interpretive signals. There's a whole set of attributes out there. So when Google goes public, or Netflix goes public, or Yahoo went public, there's all these things. Everybody's got all this information. Right? There's an abundance of information. In fact, it's sort of ironic that we talk about this as economics of uncertainty when there's like more information than anybody could possibly process, right? Then they have some model that takes all that information into some sort of prediction. So what we can ask then is, why do people have different values for Google? The reason they have different values for Google is because they look at different attributes, and they've got different models, right? And now we want to ask, in some sense, just do a calculus on those models. So the idea here isn't very deep. This is something psychologists have known for a long time. And the idea is basically this. Reality is complicated. We're not that complicated, right? So we just sort of say truck, car, chair, right? We don't perfectly define everything. We place things in categories. There's a lot of evidence that we also sort of reason from exemplars, right? So we have a few core things that we think of, and then we just sort of blow out little balloons around them in space, okay? So now we write down the crudest possible model I can write down. There's a set of objects, there's n of them, and there's a set of outcomes, which are good or bad. So basically, let's say there's restaurants here in Paris, and they're either going to be classified as good or they're going to be classified as bad. An interpretation, what I'm going to call an interpretation, is just a partition of the set of all possible restaurants, right? So I could basically take the city of Paris, and my partition could just be by all those little things you call, all little numbers. I can say anything in 7 or 4 is probably bad, right? And anything in the other number seems to be good. That could be my model. It's worked so far, right? Everything in 5 and 6 has been great. And there's going to be some probability of each of those things arising. Okay, great. So how does this work in practice? Let me give a very specific example. Let's suppose we're picking a new dean or department head or university president. And let's suppose that I've got to make this simple because otherwise, it would take too long to do. But let's suppose there's only 2 attributes to a person, which is their level of experience and their charisma. Okay? So this is the mapping of reality. If you're high experience and high charisma, you're good. If you're low experience and low charisma, you're bad. Okay? And if you're high charisma, low experience, you're bad. If you're medium high charisma and low experience, you'd end up being good. Now you could say, why isn't this all goods up here and all bads down here? I want to make it somewhat complicated, right? So it's a little bit sort of funny in terms of the story I'm telling, but I want to have some nonlinearities in there. Okay? I don't want it to be just all goods up and all bads down. So this is how reality works. But again, people don't experience the, we only saw what Joseph Conrad would say called the mere show. So what we do is we sort of maybe only focus on one thing. So I might have an interpretation that just says, look, I'm only going to look at experience. So if I only look at experience, if I see someone of high experience, 3 times I'll get good, 1 time I'll get bad. So what I'll do is I'll predict good. If I see someone of medium-low experience, I have 1 good and 3 bads, so I'll predict bad. So our basic story here is not at all complicated. People create bins, those partitions, in this case they're rows, and then we make predictions. Once I've put it into a set, I just make a prediction based on that set. And what collective wisdom is going to be is sort of adding up all of our predictions. Okay? Now remember in the statistical model we got that what matters is sophistication and diversity. Right? And that's sort of the loose thing that we all talk about mattering, and we'll see that the same thing sort of works here. Now let me make one sort of quick assumption. You can define 2 interpretations as independent if sort of one of them looks at columns and one of them looks at rows. Right? So if we're looking at different variables. You can sort of ignore the math. But if we're looking at different attributes of different variables, then they're going to be independent. Now you can also say a prediction is reasonable in this case if it's correct at least half the time, and it's informative if it's correct more than half the time. Okay? Now in these cases, it's sort of, if you have a lot of experience, it's hard to be wrong more than half the time, right? Because you could just do the opposite of whatever you were doing. Okay? Well, here's some good news, bad news. If you've got these independent interpretations, then the good news is they're negatively correlated. So remember, diversity is a good thing. So here we get this really nice thing. We get that if I look at one dimension like rows, and you look at another dimension, which were columns, and we make these predictions, they're negatively correlated, and this is the degree of negative correlation. Okay? So what we get is, if people have diverse ways of partitioning the world, their signals are necessarily negatively correlated. Right? And we just saw how negative correlation in the statistical model leads to better predictions. Okay? Now, this is an artifact of the binary case, but the same sort of effect exists in the cardinal case as well. Okay? Let me just drive this home a little bit harder. There's a lot of models, formal models, in political science, philosophy, economics, and even in computer science, where we make the following assumption. There's a set of states, good or bad, that are equally likely, and we assume people get signals, little g, little b, that are independent conditional on the state. So like the state of the world can be good or bad, and everybody gets an independent signal. What I'm saying is that's impossible if people have these models where they look at different dimensions. Now you could say, could I somehow rig it so that I get this? And Lou and I've done we have a formal paper where we show there's one function that does it. So instead of all functions, there's only one case that does it. So basically, this can't happen. It's a nice, convenient thing to assume. So it's really nice. If I want to write a paper on how do juries work, what I would do is I'd say, person's guilty or innocent with some probability. Everybody gets signals that are independent, conditional on that, which either say guilty or innocent, right? But that's sort of taking that luminosity model, so somebody's handing out these independent signals. What I'm saying is if people actually have these predictive models, that assumption can't hold. It's a bad assumption. Okay. So let me do an example then of how aggregation would work here. So here's the example again of charisma and experience. Here's our experience person. Here's a charisma person. Right? So the charisma person looks at columns. So if they're high or medium high, they say good. If they're medium low and low, they say bad. Okay? Because all they do is look at the column and they say, boy, they're a high charisma person. My guess is this person's going to be a good deed. They're a low charisma person. My guess is this person's going to be a bad deed. Okay? Now, since we're going to be voting, I've introduced a third person. So here's my third person. And every committee I've ever been on, this person's been on the committee. So this person seems to have a completely irrational model. So their model, now I've changed the letters in here. This is their model. So their model is, if you're in the middle on both things, you're going to be bad because you're boring. If you're extreme on both things, you're going to be bad because you're too extreme. But if you're balanced, if you're extreme on one and moderate on the other, you're going to be fine. Okay, now this makes seemingly no sense, but it's also right 75% of the time. That's why I've always, so you get people when you're on a committee, like a hiring committee, somebody has their theory about who you should hire, who you should admit to grad school, and you're like, this makes no sense. Well, the thing is, it might make sense. But if they're drawing from a lot of experience, it could be they're just as accurate as you are. It's just that theirs doesn't look like a regression model. Theirs is based on a whole bunch of exemplars that they've sort of blown up into sets, right? And these exemplars, in this case, create a diverse thinker who's also accurate. So let's have these people vote. If they vote, if the person's high on both or low on both, the two sort of rational people, their votes carry the day, and it doesn't matter what the weird person's doing. But if they're low on one and high on the other, then this other person, the charisma and experienced person, are going to split their votes, and it all comes down to that other person. And remember, that other person has sort of bads across the diagonal and goods that way, right? So when I aggregate the vote, I get something like this, and that's the same thing as reality. So what I get here is that the crowd's right 100% of the time. You could say you rigged this, and of course I rigged it. That's like my job, right, is to rig these things. But the rigging is indicative of a general phenomenon, which is if you have people with diverse representations and then models, diverse categories, and have models based on those categories, the aggregation is going to work really well, better than it would work than if you had independent signals, right? Because you get this negative correlation coming in. So when does aggregation work? Well, here's a way to sort of think about it. And this is in the more general case. Suppose there's some outcome function. In this area it has 1. In this area it's worth 3. In this area it's worth 2. And we're going to sort of, have some sort of prediction market or some sort of poll to figure out what the outcome's going to be. Well, suppose some person's 1 categories look like this, and person's 2 categories look like this. Well, it turns out this category is useless, right? But that's not going to matter because they're going to bin these things separately. But so what? They're going to realize that they've all got basically about the same value. Now, neither one of the people has this box for 2, but the intersection of these two things will give them this box for 2. So even though no one has it exactly, by each of them voting, some contribution to it, they can sort of get this thing right. So what you've got here is you've got sort of sufficiently diverse people and sufficiently sophisticated people to get it right. But here's a case where you've got lack of diversity. So here these people are both reasonably sophisticated, but one's sort of a subset of the other, and there's no way they could get this function right. Right? Because no one has a separate box for 3. And no sort of intersection of the boxes would work. Right? You can also have, here's a case where these people are sort of maximally diverse, like the charisma case, but they lack appropriate sophistication. Right? So the way you want to think of this is you want to think of each person has little sort of boxes, and they can assign value to their boxes. And then when we vote, we're just sort of adding up the weights in all the boxes. And what we need is we need the weights in those boxes to sum up to the value of the functions. Right? And if that doesn't happen, you can't get wisdom of crowds. Right? If it does happen, then you get the wisdom of crowds. So how do you formalize this? You formalize this in sort of an ugly way. There's a notion, if you can think of sort of what we call collective measurability. And what you need is you need the outcome function, and this is formal sort of math. It's just that it's measurable with respect to the smallest sigma field at the M are measurable. What that just means is if I take intersections of those sets, right, then I can write the function in terms of those sets. Okay? So it just means I can basically write the outcome function as some function of the little sets that the individuals have. Okay? Now, if I'm just going to use a market or a poll, then it's got to be the case that this function is a threshold function. This is what we call additive separability. Okay? So if you're going to have some sort of prediction market work or a poll work or voting work, it's got to be the case that the function sort of only depends on the sets, and it's got to be the case that the function's a linear function of those sets. Okay? So you can prove the following: is a classification problem can be solved by a voting mechanism if and only if it satisfies those two things. Okay, so it's not only sort of loose intuition that it's got to be sort of those sets, and those sets have to add up in a simple way. That's a sufficient and necessary condition. It's the only way you can get collective wisdom. So let me say this in a non-technical way. The collective can only get it right if any variable or interaction of variables that matters is considered by some combination of people. Right? It's easier if it's by one person alone, but sometimes you can have a combination of people sort of do it. And the outcome has to be written as the sum of those individual models. So you need, right, a lot of diversity in how people have encoded things, and you need those people to be sufficiently sophisticated that you can sort of add up what they're doing. Okay, 5 minutes, I'm in perfect shape. All right, so what does this mean? Well, it means if you've got small groups and people have sort of endogenous model creation, so they have to choose what information should I get, what model should I produce, then you're likely to get very different models. Because I'm going to think, I'm on a committee with you and you and you, and I know how you think, so I should think of this world in this other way. And if that's the case, you probably should do better than the statistical model would predict. But if I think about 2 million people voting, or even 100 people voting, or when John was talking, 700 people in some constituent assembly, there's no way we're going to get 700 independent models probably, unless there's lots and lots of variables in play. Okay, so what are the effects of sophistication? In the generated signals framework, in the statistical model, sophistication really doesn't have much of effect. All that does is lower the error term, right? And so it just makes it a little bit more accurate. But in an interpreted signals model, increasing sophistication has a huge effect because it basically means you have smaller sets, right? So people have finer and finer little partitions, and so they can just predict a lot more models. Diversity has two effects, and this is where one of the things I think it's really worthwhile is to think about unpacking diversity. So one way diversity has effects is you can just have diversity in the variables you consider, or diversity in the sets you have, right? So in the thing I had one person looking in columns, one person looking in rows, and one person with this weird thing, right? I don't know who that is. But it can also be the case that there's diversity in what we call perspectives. And this is some work that Lou and I did 7 years ago. And here literally differences in how you represent the world. So like polar coordinates versus Cartesian coordinates. Let me give an example of this. Here's a really hard function, right? So it's 2x plus 2y plus z minus 2xy. You'd figure no way could simple people voting get this right. Here's my three voters. Voter 1 model says, I just look at x, and I just give the value for x. Voter 2 says, I just look at y, and I give the value for y. Voter 3 uses something called the Walsh functions. Now, these x, y's, and z's are just 0, 1s. And she says, if there's an odd number of bits that are value 1, I say 1. If there's an even number that are value 1, I say 0. So she just counts the number of bits. That's a completely different way of encoding binary strings, but that's just how she sees the world. Okay? So that's not like, it boils down to sort of parsing things in a different way, but it's literally a different representation of reality, which is based on what they call parity functions in computer science. Let's watch what happens if we have these people vote. If I have 0, 0, 0, person 1 votes 0, person 2 votes 0, right, because there's a 0 on x and a 0 on y. Person 3 votes 0 because the number of 1s is even, and f actually has a value of 0. If I go down to something like 1, 0, 0, person 1 votes 1 because there's a 1 there. Person 2 votes 0 because there's a 0 there. Person 3 votes 1 because there's 1, 1. If I add those up, I get 2, and that's also the value of f. So this works, right? Now you could say, how in the heck does this work? Here's why it works. If I take voter 3's very simple model in a different representation and write it in the XYZ representation, it looks like this. Why? Because let's suppose what it's saying is if x equals 1, this has to equal 1, right? So I get a 1 there and I get zeros everywhere else. If x and y both equal 1, I've got to get 0. So I get x plus y, so I've got to put a minus 2xy, right? So this is just the way of mathematically writing down this simple rule. So what you get is if somebody sees the world in a different way, that can actually be translated into an incredibly complicated mathematical representation in the common way of seeing the problem, right? So this is why it's sort of politically correct to say diverse perspectives are valuable, but it turns out if you think about it, if you go to a computer science department and say, are diverse representations of binary strings useful? That's like asking a physicist, is gravity keeping me on the ground, right? Because, they're constantly trying to think about how do I represent this problem, right, in order to simplify the problem. So diverse representations are extremely useful. Okay, last point, then I'll summarize. An interesting thing here is there's a lot of results that regression beats individuals, right? So whenever they've compared experts to simple regression models tend to beat individuals. Well, part of what I think is going on in the wisdom of crowds is like this result. Because think about what's going on. When we add up these individual models, either through voting or weighting, we're getting some sort of approximation of the underlying function. If people are sophisticated and diverse, that model has lots of terms in it, right? And lots of interaction terms. It's got a lot of variables in it, right? The weights on those variables probably have the right sign, but they probably don't have, and they're probably correct loosely up to orders of magnitude. Again, if you've got a lot of sophistication and diversity, and these models are reasonably good. And you get this nice thing that the crowd can include all sorts of models, all sorts of variables, but not overfit, because no one's taking into account all the variables, right? So if Pasquale takes in 3 variables and I take in 3 and Karin takes in 3 and Gary takes in 3, between us we might have taken in 12. There might not be enough data to do 12 variables, but none of us is individually overfit, right? So when we add them up, we get sort of a lousy 12-variable regression, But one thing we know from a lot of experience is lousy 12-variable regressions do pretty well, right? So in some sense, you can think of, in this way of thinking of things, the non-statistical way, the cognitive way, what you're thinking of is the crowd is a bad regression. Okay, so quick summary. Interpretive signals have different statistical properties, and it's a different way of thinking about aggregation than these sort of things handed down from God, right? You cannot get what's not in an individual's model or in some additive combination of people's models. So there's no free lunch, right? But it is the case, though, that somebody seeing the world in a different way or a bunch of people parsing the world in a different way does sort of give you a free lunch. And diversity and or sophistication seems to be key to aggregation. If you want to think about endogenizing this, it seems like you want to encourage people to be engaged but different. And this is what they do in ensemble learning theory and computer science. Not only do they train models to sort of predict correctly, they train them to predict correctly when the other models are wrong, right? So it's almost like they've read your book, Brian, and they sort of think, if everybody's getting this thing wrong, then they give a huge payoff function for you to get it right when everybody else is getting it wrong. And so then when you add that person to the crowd, right, it induces negative correlation. Okay? So there's two things that I've left out. Is that clearly social interaction could improve models if people refined their partitions. If by, one reason we go to conferences, right, is to, in some sense, refine our partitions, right? So if people by interacting can make finer and finer sets, then our models are going to be better and the crowd will do better. And then the last point, sort of funny saying this is left unsaid, but the implicit argument, the sort of subversive thing I'm trying to do here is a lot of what we call uncertainty in the social sciences, like we say there's a lot of uncertainty about this variable, I think is really actually cognitive diversity, right? That we live in a world where there's an abundance of information, and we're trying to think about what's going to happen in this election or this football game. It's not that we're getting uncertain signals from a distribution. It's that we're overwhelmed with information. We're bringing cognitive diversity to bear on that problem, and we're coming up with different predictions. And the point is the statistical properties of diversity are different than the statistical properties of uncertainty. All right, I'm done. Thank you.
So there was an awful lot packed in. I enjoyed reading the paper, albeit in a slight rush in the end, but there's an awful lot packed in there. And Scott started out by sort of claiming that some of this was pedestrian. I think it's a really interesting paper. And what it does is it explores formally the conditions for a crowd to be wise. And as a corollary, it sort of tells us when we might expect a crowd to display madness, which is also something that's receiving increasing attention now, sort of as the hype settles around this issue of collective wisdom. So it's a timely piece of analysis. There's considerable buzz surrounding collective wisdom still, but we have really very little formal understanding of when we really can expect the collective to act in a smart way in terms of the predictions it forms in this context, or possibly the way in which it sets about solving problems, and when we might expect to see a display of madness. And there are many, in Scott's paper, he mentions many real-world examples of apparently bad crowd decisions. So we might think about a jury verdict that seems very obviously out of kilter with the underlying reality. Or we might think about market valuations of assets that exhibit a bubble nature and sort of seem out of kilter with reality also for some time. And so this has a real world relevance that I think is very obvious. And so what Scott does in the paper with his co-author Liu Hong is he briefly reviews a statistical model which has sort of dominated the social sciences literature on collective wisdom, if you like. And he then goes he shows that through this model we can get some sort of some interesting now standard results about collective wisdom, and but he then basically moves to develop a if you like a more sophisticated cognitive model of collective wisdom, which he suggests, and I would agree, offers deeper theoretical insights into the topic. And key insights from that modelling exercise are that individual sophistication and expertise matters. If we are solving a problem that involves a finer categorization than the crowd can be expected to produce, then it can't be solved via any mechanism, so whether we consider voting or prediction markets or whatever. And but perhaps less obviously, collective diversity matters. Individuals can be thought of as carrying around in their heads at any point in time a predictive model, and these models must differ sufficiently. The crowd must be sufficiently diverse for collective wisdom to be realised. And so the most capable crowds then comprise individuals who are both individually sophisticated but also quite different, sufficiently different from one another. I'll just very briefly review this because I want to move. Obviously, Scott's spent quite some time developing at length the insights from the paper, but he reviews the statistical model of collective wisdom. He's careful to. He classifies the signals that individuals are assigned in these models as generated signals, and he points out that quite often in the literature these are assumed to be independent signals and unbiased and so on. And he points out that this, and you made this point, I think, to conclude as well, that quite often sort of uncertainty really might be the assumption of uncertainty and sort of independence in these signals might really be sort of getting at diversity underneath it all. And so we might be building in diversity implicitly into these models, but not really explicitly dealing with that. And in that sense, his contribution with the cognitive model is very welcome. So I'm just going to move on to that. He also points, he uses this bias, variance, covariance, decomposition of a slightly more generalized statistical model to show that negative correlation is important, because then, of course, that's relevant to the insights he establishes with his cognitive model. And so the cognitive model allows for deeper theoretical insights. So now we've got a slightly more sophisticated cognitive representation of individuals. A person has their own personal interpretation of how things really are. They partition states into distinct categories. And these categorizations could be fine or coarse, and you might think of an individual as sophisticated or less sophisticated in those terms. And these predictive models that individuals carry around in their heads, they're an attempt to approximate some outcome function. And the output of this individual's prediction model is her prediction. And Scott and Hong adopt the terminology interpreted signal to distinguish this form of signal from a generated signal. And he emphasizes that these interpreted signals, and this is really key to the results from the cognitive model, these interpreted signals are likely to have different statistical properties. Most importantly, they're likely to be negatively correlated, okay, which is good from the perspective of the prospects of collective wisdom. And in this sort of setup, the average of the individual's prediction, perhaps the unweighted average, would be the collective prediction. You might think about weighting and so on, and that raises its own issues. Yeah. It's interesting to think that the cognitive model, unlike the purely statistical model, might imply probable limits on diversity, even when the team size grows very large, whereas you can just keep throwing people into the standard statistic setting, and that kind of helps, and these errors cancel out, and eventually you've sort of got truth. So a few personal reflections on the paper, fairly unstructured in no particular order. I think as I've said already, I think it represents an important contribution to the literature. It's encouraging us to in our modelling to consider explicitly diversity. Often this is sort of swept to one side, or it's noise, or it's perhaps even just not dealt with in a sort of in a way that's helpful when we understand these insights from the cognitive model, particularly. And he, Scott and his co-author set out a formal framework for distinguishing and considering the relative contributions of diversity and expertise to the collective wisdom or the collective madness, and thereby demystifying the possibility of collective madness. So it could be that the predictive models are just too similar, and you're just throwing in people whose models overlap, and eventually you end up with some sort of collectively mad outcome. And so these micro-foundations, I think, offer us a very valuable step towards developing optimal mechanism design insights. So we might want, quite reasonably to think about particular cognitive tasks and what is the appropriate aggregation mechanism for that setting, and so on. And so I think I see this as a very valuable step towards that goal. Very interestingly, it has the model and its insights, this cognitive approach, has far-reaching and intriguing, I would say, policy implications. And I just want to share a few of my suggested implications with you. So you might say, well, a sort of, without getting into the optimal mechanism design in a kind of formal way, you might just say, well, it seems from this sort of modelling approach that we want our teams to be expert yet diverse in reality. But how do we operationalise this? What does that really look like in reality? And so you might think about, and I think you mentioned this as an example in your book, where I've drawn the motivation from. You talk about the implications for school admissions. So there, you could end up with the situation where instead of just maxing individual ability and letting people in through the door, strictly ranked according to individual ability, you actually start to sacrifice some of that on the margin in favour of heterogeneity. And I think that's a really interesting thought experiment. And you might think about implications for the human resource policies more generally in the public and the private sector, so corporations, government, institutions, and so on. So it could be that some of the existing policies you might want to overhaul thanks to some of these insights, and it could be that other policies that are already in existence are actually more intelligible and alternatively rationalised through this framework. So you might think about policies that we see in corporations like...
Time is up.
Okay. You can read.
You can briefly.
Okay, so very briefly.
Summarize.
So very briefly, I've highlighted three possibilities here. We see in the real world sort of rotating of staff, and sometimes, I've heard from friends who've been sort of on the receiving end of this policy. They don't understand why they're being moved to a new team. They've only been in a particular team 6 months and so on. And they, sort of justifications out there in the field seem to range from sort of, they're trying to make sure that no one individual is indispensable. They're trying to encourage us to bond with others in the firm, get an overview of how our firm's really working at the high level and so on. But it could be, thinking about Scott and Lu Hong's model, it could be that this is, a sort of a rational attempt to trade off the benefits of having a team that has a sense of togetherness, a common language with which to operate, and so on, against the benefits of ensuring diversity and preventing excessive convergence in the predictive models. So you talk towards the end of your talk about social interaction, perhaps helping individuals refine these models, but it could be that they converge through dialogue.
Right.
That's a possibility. A really interesting thought is that you might want, in some settings, to think about the individual's contribution to team diversity at the both at the recruitment stage, but also when you're thinking about rewarding them and promoting them and so on. And of course, that raises, the very important question of, will this be perceived to be fair and so on? Meritocracy is understood to be, sort of promotion based on individual ability and demonstration of that individual ability. What about contribution to a team-level diversity? What if I go out and acquire a very diverse, a very different model that sort of very well complements the existing team setup? Should I be rewarded for that and so on? So then you can get into thinking about, if you're an economist, you get into thinking about incentives for creating the right incentives for diverse diversity in models to arise. Okay.
Thanks very much. That was a fine presentation. Now I'm going to ask you to, with hypocrisy, I'm going to ask you to state your question within 1 minute. And I have David Estlin signaling me earlier. It's not because he's my friend. No, he raised his hand 15 minutes ago.
I knew my question already. Is this on?
Yeah.
Okay. I may be totally wrong about this because I'm not mathematically sophisticated, which I know is an asset in a group decision making. I'm puzzled about diversity. Yeah. So,
this one works.
I'm puzzled about diversity. So, suppose that there's some future fact that I want to know the answer to, and I'm hoping to solve it through some collective wisdom thing.
Right.
So I take some bunch of people in this room and I look at their models, and they don't look very diverse to me. Looks like they agree with each other quite a bit. And so you say, diversity is a good thing.
Right.
Can we conclude from your arguments that I should now bring in some more models to make it look more diverse? And I think the answer is no. Because if I may be wrong with this, if I understand you right, what I need is nothing that answers to this generic idea of diversity. What I need is a very specific thing that I can't produce unless I already know the right answer. That is negative correlation. Negative correlation is if somebody tends to be too high, I want to add somebody that tends to be too low to the same extent, oversimplifying a little bit.
Right.
But I can't get that unless I already know the right answer because it's relative to the right answer. So I can't do something like just increase heterogeneity, increase diversity, because I wouldn't know whether I'm actually balancing them off relative to the right answer or making things worse. Is that right?
No, not quite, because the thing is that let's suppose, suppose that there's 8 variables, x1 through x8 that people have in their models, and you notice that there's 10 people that look at 1x through x4 and 10 people that look at x5 through x8, right? it'd be very easy to say, could somebody go out and have a model with x3, x4, x5, x6, and somebody come out with a model with x1, x2, x7, x8? Or you can construct those models with regressions or something if possible, right? And these would give you diversity, and you can show, as long as, it's mathematically pretty straightforward to show, as long as these variables are of predictive value, then they'll necessarily have variance. They'll be negatively, they'll necessarily bring negative correlation in.
Okay, so my question was I wasn't sure how diversity was defined so that you could say something like, if you add diversity, you'll get negative correlation.
So in the case of...
Is diversity defined here as having different categories?
Right. So you can. So in the one case, if we're actually looking at different variables, and it's a binary prediction, then somebody adding a new variable necessarily gives you negative correlation. I mean, that's what the theorem said: the 1 minus p squared thing. Another variable that's useful. So you can't take into account hair color of the point guard, right? And have that be useful in terms of predicting whether the team's going to win a basketball.
Okay. Well, that's very helpful. There's still this bit of the worry left, which is you need a very specific kind of diversity. You don't just look through the applications and look for different kinds of people. You need something, and I'm not sure exactly understand what it is, but something very specific. Well,
no, but the thing is, think about it. It doesn't make sense to. I think how we normally think of diversity is we think, we've got an engineer, we've got someone from this identity group. I mean, we can't expect vocation or identity group to somehow map into magical collective wisdom, which I think a lot of people somehow, when they say diversity, is right.
That's what I want to be clear about.
Right.
Yeah.
So what has to happen is it's got to be the case that somehow what you're really getting when you add up those models is the sum of those models in a way. And if it's a market, you're getting a weighted sum of those models. And so what you'd like to have any variable that, variables that are relevant included, and you'd also have the interactions that are relevant included, right? In some sense, you'd like to somehow get a big regression. Now you could say, why don't I just run a regression? Well, the thing is, regressions only work if you're dealing with something that's happened you've got a lot of data that's happened in the past, right? So the fact is, if you're predicting something new, you might not be able to rely on regressions, and so you're relying on sort of instinct.
Okay, thanks.
Right?
Professor Kaplan, 1 minute.
No problem. Going back to your example where you had the 3 different voters guessing, and you had the third voter using the bizarre rule, which turns out to be exactly the rule you need.
Yeah.
I think I have some idea what you'll say, but I just want to hear you explain it in a little bit more detail. Suppose that voter number 3 had a rule like had a rule like he always guesses a million, or he guesses 10 times X. Where would that? How would that actually fit into the framework that you're talking about? Would that just be very low sophistication, large diversity, and the sophistication outweighs the diversity?
Yeah. So two things. In that example, it's a classification problem, right? So you're either voting good or bad, and so given any categorization, you can assume that someone's always going to be reasonable because you can't be. If you've got enough experience, you can't be wrong you'd be right more than half the time. So the point is, if you take a go home and create 5 by 5 boxes and just draw random sets, draw just 5 random partitions and have the people vote, and you'll be like, man, they keep getting it right. They keep, so it's as long as when I create the little box, like if when I do it and create the little box, my shock has escaped me. As long as if I have a little box with 4 things in it, if there's 3 goods in there, as long as I make the prediction good, right? So I'm assuming that the people are smart. If the people aren't smart, if you have them making the wrong prediction, then crowds will get it wrong. But and that's what we should expect, right? So the point is, the mathematics would somehow be misleading, or we'd have rigged it if I were showing that crowds always get things right. What I'm showing is that people who make sort of the best prediction they can make given their category. So that's the implicit assumption I'm making. If you make the best predictions you can make given your category, those categories are reasonably fine, and they're different, and they slice the world differently, collectively you're going to get things right.
Just a quick follow-up.
Yeah.
Yes.
So what would you say is the correlation between diversity, as people normally use the term in the modern world, and diversity of the valuable kind that you're talking about?
Oh, so I think that's a totally empirical question, and it depends on context, right? So,
but are you willing to guess? Or?
I think it depends on, I think on hiring and admissions decisions, I think that there's probably a reasonable correlation. Just because anytime you're identifying characteristics of people, right, then I think people who've had different life experiences tend to tend to view the world and view other people through their own life experiences. And I think that those things do probably correlate. When you look at sort of predictions, I've looked at things like NFL draft, NBA draft sort of things, and also like federal open market, people predicting interest rates. And if you look at things like, what school they went to, or that stuff doesn't seem to matter at all. The problem is it's hard to get data, it's hard to get huge data sets of lots of people's predictions. One thing that's going to be great, as companies that are using these prediction markets, they're actually figuring out who's negatively correlated. So one of the beauties of prediction markets, right, is suppose I run a prediction market in my firm, I've got 300 people participating. Now I've got to put together a committee to decide something. I can then look and I can realize that, you and Gary have been really negatively correlated and both been pretty accurate. I want you two on my committee, regardless. And if it turns out you're different entity groups, great. But and then, in some cases you will. I mean, my own experiences I would say my own experience is Michigan that departmental discipline and identity do correlate with very different sets of categories, right? If I take economists that all went to the same school, they tend to categorize things similarly.
Keep the economists to a minimum.
Yeah.
So when you have, as you said, the diversity and individual skill, we might call it this kind of sophistication or skill, are both as important. So if you have a group of people who are initially very diverse, and they work together on a team or something, and they will tend to grow less diverse, but perhaps with the confrontation become more skilled individually. So as long as that transfer is done in the right way, I guess the group remains as performant as it should. But do you have a way of measuring, perhaps in different situations, perhaps on the stock market, wherever, measuring when diversity becomes catastrophically, dangerously low?
Yeah, so two quick reasons. So Blake LeBaron has done some stuff where he's got artificial stock markets. He's got automata trading. And when he gets bubbles and crashes, he can actually, these automata are like little machines that have a bunch of models in their head, and they use the model that's working best. So each little trader has like 10 models, and whichever model's been doing the best over the last week, that's the one they've used for their trades. And he can then plot he basically uses the entropy or the variance in the trading strategies. And what he sees is that right before these crashes and bubbles, there's a massive reduction in the amount of diversity. So you can, but the thing is, it's very hard. If I were looking at real stock market data, there'd be no way unless I could pry open the heads of the traders. But anthropologists use this technique called a pile sort. Where what you do is you give people a set of words that are relevant for their environment. So you might give people a set of food items. That's the example I always give. And then you ask people to put them in categories. Now, if everybody puts them in the same categories, right, then that's suggestive of the fact that there's, this is called the cultural consensus model, that there's a strong cultural consensus. So one thing that firms can do and organizations can do is you can just ask people, here's your 50 suppliers, or here's your 20 competitors, or here's your 60 markets. Put these in piles. And if everybody puts those in the same piles, then there's really only two possibilities. One is it was an easy exercise and they're obvious piles and everybody got it right and you're just operating perfectly. And the other option is you're suffering from groupthink and you can make some really bad decision. Right? So you can... So I think the anthropologists are way ahead of the game on this one, but I don't think that's been used very much yet in organizational theory.
A final question from Professor Vermeule.
Thanks. I don't know whether Karen will agree with this or not, but I just want to say I think the implications for institutional design are not clear because collective wisdom is, of course, not the only thing we care about, right? We don't want to maximize collective wisdom. We want to optimize it, right? So suppose that collective wisdom systematically trades off against other things like the direct costs of making decisions because diverse groups can't talk to each other or get an argument or whatever, or the opportunity costs of making decisions because they argue interminably or whatever it is. There are any number of institutional factors, so we can't just move from collective wisdom to institutions in the real world. That's all.
No, absolutely. And the thing is, but I think the point is you want to enlarge the set of considerations you have, right? So, for instance, let's take the Federal Open Market Committee that sets interest rates in the United States. I mean, they have 18 cookie-cutter economists in a way, right? But Bernanke had a meeting in Princeton last week with all these funky people who study bubbles, right? Which is evidence of the fact. It means he's aware of the fact that he's around a bunch of people that are all thinking in the same way, and they all missed a big bubble. So I'm going to bring in anybody with a PhD in physics who's thought about bubbles, and just see what they think. So I think that it enlarged, and especially within political science, and other people here can speak to that better than I can, but when people have thought about bringing different groups in, right, in issues like minority representation, it's been entirely thought of in terms of preference, having their preferences at the table, and not, as Jon was saying, their particular set of knowledge, right, of a set of issues on the table, at the table. So, having women at the table when you're deciding some welfare policy would seem to make a lot of sense, right?
I should say, I certainly would agree, with that caveat. One of my concerns actually with the sort of current discourse around prediction markets is that the focus is too narrowly on sort of average accuracy in some sense, and really what we want to do is step back from that and say where to this information and this collective wisdom, what use do we want to put this to, what are the alternatives, what are the costs and benefits of all of these different things, and set this very clearly in that frame. And I think that possibly you get very different answers depending on the context, but it's obviously interesting also to consider accuracy and the conditions for collective wisdom, which is what Scott does.
Yeah.
Well, let's thank Scott and Karen for
That was great.